My name is Day1-05. Very happy to chair this session, which is about very broadly about game and VR. There are 4 papers in this session. The first paper is titled Mobile Game for Crowdsourced Molecular Docking Pathways by Chavez, Torin, Adamson, Lydia, Tapia, and Bruna, Jacobson. And the paper is going to be presented by Chavez.
Hi. So, as I said, I'm Chavez. I'm from the University of New Mexico in the United States. And Torin Adamson, my PhD mentor, is also here with us today. I'm here to talk about a game that we developed to help solve a really difficult problem in biology called molecular docking. So first off, crowdsourcing. Mobile devices are really good for this because they're ubiquitous. Almost everyone has one, and recent studies show that mobile platforms are the most common platform to play games on. So, okay, sounds good. Mobile devices are the most common platform to play games on, and so this makes them a really good platform for collecting crowdsourced data on. Now, crowdsourcing has benefited problems in biology and other disciplines before, and something that's common is that people have been doing to capitalize on this is taking specific complex problems, like in the case of protein folding, and creating a scientific simulation and gamifying that. So there's gamification elements. People want to play this game, help collect data about a hard problem, and then that data that's collected can be used to help solve it. So the problem that I'd like to talk to you about today is called molecular docking. Molecular docking is an open problem in biology. We don't have a solution to it. And it involves a ligand, a smaller molecule, and a receptor, which is a larger protein, usually on a cell membrane. And when these two things bind together, the ligand is said to be docked. And this binding process drives a lot of biological processes in our bodies. This is how we taste, how we smell. The immune system uses this process to function, and it's also how allergies are triggered. So understanding how this works is really key to developing new medicines and developing new drugs. So the pharmaceutical industry would love to screen lots of ligands and receptors and figure out how these things bind together. And we want to learn the binding site, how these things bind together, and a path that the ligand might take to reach this bound state. But this is a really difficult thing to do. In the lab, if we screen lots of different things physically, it can be really expensive and time-consuming, and because most of the tests ends up being negative in the lab. And there's also simulations for doing it, automatic simulations, but as you might imagine, that's also really computationally expensive. It takes a long time to run. And there's also 3D simulations, virtual reality simulations, where people can try and put these things together. Now that's looking at this idea that something that humans are really good at. We can take these two things and look at it a little bit like a puzzle game. These two things fit together in some way. We have the interaction energy to guide us. Unplanned intermission. It said it had lots of power. I'm so sorry. I also have a power cable. I'm sorry, it said it had lots of power. Is there a place I could plug it? US plug, but I don't have a converter. You have a converter? Oh my gosh, thank you. So this is the wonderful thing about technology. When it works, it's fantastic. So much. This is US, right?
We all thinking about this problem. Very good job. Difficult.
And I can talk some without my slides. Oh my gosh.
So it's going to come.
Okay, we have backup. See, this is why we plan ahead. Okay. Right here. The other side. Right here. Okay. All right. Thank you guys so much for your patience. All right. So this is a difficult problem, but we figured out that it's a lot like a puzzle game, and humans can help solve puzzle problems. We're really good at looking at the surface of the receptor and figuring out how these two things might bind together. And that's something that's really difficult for a computer to analyze a surface like this and find that. And so in our lab, a number of years back, we developed a molecular docking game on a commodity device, laptop hardware that you might be able to play at home. And we presented that here in MIG back in 2014. And we really thought this was a great idea, but we really wanted to extend this to mobile devices. So I would like to present, it's supposed to be, there we go, okay, awesome. This is Dock Anywhere. This is a mobile molecular docking game that allows you to try and work on docking the ligand and the receptor on your mobile device. You can explore the interaction energies between these two molecules in real time, again, on a mobile device. So this is really neat. So when we were designing Dock Anywhere, there were a few things, a few design objectives. Okay, might be the HDMI cord. I'll just tap it preemptively. So there were a few different goals that we had in designing Dock Anywhere. We wanted to consider a control scheme that was both intuitive so people would want to come back and play the game, and allowed people to collect low energy states, because we know that the ligand and receptor will bind in the lowest energy state between the two, so we want to be able to find those states. We want to be able to collect those states so we can use the data offline to try and solve the problem. We wanted to gamify the simulation, so again, people would want to play the game, and to motivate them to find those low energy states. And finally, we wanted to adapt this to a mobile gameplay environment, specifically remembering that mobile gameplay sessions are usually shorter than desktop gameplay sessions. So we wanted to make sure that we consider that. Now the first challenge was the controls. So this is a really complex problem, computationally speaking, and so we reduced it already by using a rigid body simulation rather than using these models flexibly. And so then we only have 6 degrees of freedom, but 6 degrees of freedom is still difficult to come up with a control interface for. We went from using a haptic device or an Xbox controller from our previous paper, our previous experiment, to a 2D touch interface. And we had to figure out some way to translate these controls. And what we ended up doing was creating a series of gestures that the player can use to control both the camera and the ligand. And they can switch between these gestures by double tapping the screen. And those gestures are 1 finger drag to rotate, 2 finger drag to translate, and 2 finger pinch to zoom. We found these to be fairly standard on a lot of programs where you had to manipulate both a camera and an object in 3D space. There's also a couple buttons. There's an undo button to allow the player to explore without the fear of losing too much of their score, so they can move back. And there's also a gradient descent button. Now what this button does is it enables an algorithm that looks at the forces between the two molecules, and it'll pull the ligand along the strongest force that the ligand feels. So if the user gets the ligand to an area where they feel like is a really low energy state, and they press this button, it'll allow the ligand to kind of pull down to the bottom of that negative energy bump. So it's a useful assistant for players. When you're playing the game, you want to know how well you're doing. So we implemented a score. This is based directly on the energy. Again, we're trying to minimize the energy, but that's kind of counterintuitive. So we created a score that goes higher the lower the energy is. And of course, we record the player's high score, and we have this bar here that fills up the closer your current score is to your high score. And we also give the user vibrational feedback, because haptic feedback was really important in our previous work. We wanted to be able to allow the player to feel the interaction energy somehow. So as you're moving the ligand around, if you're trying to cram atoms into other atoms and they're colliding, you'll feel it because the device will vibrate. And finally, adapting this into a mobile gameplay environment. Because mobile gameplay sessions are shorter, we wanted to make sure that we had saving and restoring the game implemented. And then we also wanted the user to be able to pick up where they left off. So we saved their best state, which is displayed as a transparent ligand. And this allows them to further explore a certain area if they think they can maximize their score here, or if they feel that area has been fully explored, they can explore somewhere else. So when we put all these components together, it's got this, I believe. When we put all these components together, this is what gameplay looks like. You move the camera around to explore the space, and this is the duck pond at the University of New Mexico. So for our skybox, you have some sense of orientation. You can rotate the ligand with a single finger swipe, translate with a two-finger swipe, and pull the ligand closer or further away from you with a pinch. And so again, the player is trying to find the lowest energy possible, and the score only reflects once you get into negative energies. And so as the player gets closer to the molecule, you see some of they found some negative energy states, so it showed them the score, and they use the gradient descent function to try to maximize their score as following to a lower energy. So once we developed Dock Anywhere, we had some questions. We wanted to know, does the control scheme allow players to find low energy states, and will the samples allow us to construct low energy paths? So we conducted a pilot study. 7 players, open gameplay, 3 different environments that we implemented, and we did this over the time span of a week. And we collected those states and plotted them, and this is what they look like. So this is color-coded according to the player that collected the state. And each one of these dots is a 6th degree of freedom state of the ligand. And on the x-axis, we have the root mean squared distance to the known bound state. And on the y-axis, we have the potential energy. So this is the start state where it starts when the player loads in the molecule, and this is their goal. This is the dock state. We can also, to have something to compare this data to, we can also sample the state space, there's the words I'm looking for, using a Gaussian distribution around the node bound state. And when we filter that by the potential energy, this is what we get. And there's a really hard to explore region here for both the Gaussian and the player data, and that's because those places are really high energy states. The ligand would never naturally go there. So we end up having this area that's hard to explore. What we noticed is that the Gaussian samples more widely, and the players are focused on finding low energy wells, which is what we motivated them to do with the score, so that's good. Next, we wanted to be able to figure out how the ligand might get to the bound state. And so we connect these points, these data points that we have based on distance, and weight the edges with by the potential energy difference. And when we do that, we can generate shortest weighted paths using both these data sets. And those are shown here. The Gaussian is in a straight, the solid black line, and the player data is used to generate the dashed line path. And again, we have distance on the x-axis, and on the y-axis, we have potential energy. And they're trying to get to this red dashed line, which is what we know is the native energy for these systems. And what we can notice here is that the path generated by the Gaussian data is a little bit higher energy overall, and the data that we collected by the players allowed us to construct a slightly lower energy path. And the other thing is that even though some of these players didn't find the negative state themselves, their data was still able to be used to construct this path. Again, the nodes reflect the player that collected them. And this was true for all 3 of the states that we looked at. All 3 of the stages, sorry. So we can conclude from this data that Dock Anywhere is effective for crowdsourcing molecular docking, at least from this basic pilot study. Because participants were able to find low energy states, and we were able to construct low energy paths from that data. Now, in the future, we would like to continue developing this game before we deploy it to a wider audience, which is our ultimate goal: get enough data, construct shorter distance, low energy paths. So we want to add more gamification elements. We want to add a motivation for players to explore more widely and not just deeply, because we want to explore this state as fully as we can with informed information. And we like to also implement things to motivate people to play, like a leaderboard. And finally, we want to be able to address this energy barrier. Again, these are really high energy states. And we believe that addressing molecular flexibility in some form will allow players to be able to explore that state a little further. So, thank you very much for your time and attention. Do you have any questions?
Microphone is coming to you.
Thank you. Thank you for an amazing game. So, because I'm an undergraduate student, my opinion may be naive. And I want to ask a question. So you designed this exciting game, right? So this is game, right? Game. I mean, game is honestly it's for fun.
Mm-hmm.
And I think that if they don't think it's fun, they might not devote themselves into the gameplay. So, I mean, for example, while they're playing your game, if they don't think it's fun, then the performance of them might be different.
I agree.
And do you have any mechanism to deal with this problem?
So specifically here, we really wanted to make sure that the data we were collecting from the game would contribute to solving this problem. Because if we weren't getting data that would help solve the problem, then the point of the game was void. So right now we've implemented the simplest of gamification methods, which was the score and a control scheme that allowed people to actually play. Adding more gamification elements is definitely something that we want to do, because you're right, we want to be able to motivate people to play this game. So we want to implement like a leaderboard and potentially some other in-game rewards. Those are all things that we're exploring. But now we know that we can actually collect the data that we need. So that's the step that we're on right now.
Thank you.
You're welcome.
Okay. Time for one more question. Keep the question short, if possible.
Thanks. As far as camera controls go, have you experimented with maybe using the device's orientation to have sort of an augmented view of the receptors?
We haven't physically experimented with that, and the reason is using the gyroscope, the motion controls on the phone, inhibits your ability to actually see what's going on. And so like if you could move around the space like this, that would work. We have this thing that doesn't really have an upside down. And so it would be interesting to explore, but we haven't yet for that reason, because we don't want our players like have to manipulate themselves in random positions. We want this to be something that they can play on the bus while they're traveling to work. Thank you.
Okay, so we thank the